Wow, what is going on in this network? As you can see, all of these lights are flashing right now, and man, this is not going well at all. My computer fans are spinning up. Something is not right here. Let's have a look at what's going on. Oh, wow. It looks like all of these packets, all they're doing is just forwarding to the switches, and this is in turn just creating a broadcast loop. So welcome back to the channel, everybody. I'm clearly in a new setting. I got a new mic down here, and sadly I will not be able to demonstrate this on the physical hardware today because I've moved out of the LAN Lab. Don't worry, I've ordered some Cisco and UniFi switches so I can practice on and continue to demonstrate how to work on actual networks in real life. But for this video, I will only be demonstrating it in Packet Tracer and a cool little virtualization software called Cisco Modeling Labs, or CML for short. But in this video, we're going over spanning tree protocol. And as you noticed, all of these packets, they just keep forwarding to each other and they never stop forwarding to each other. And I don't know if you heard, but my fans on my computer were spinning up because it just kept going and going, and it was overloading my CPU. So how does this work? Basically, all these packets, they're just sending broadcast messages to each other because that's really all switches do. All they're going to do is forward data. Doesn't matter what data gets to it. They just want to send it to the next MAC address. If they're not connected to like one of these IP addresses or one of these MAC addresses, they're just going to keep forwarding it. And that is what's happening here. So the cool way we solve this is a little protocol that was invented in, I think, 1985. It's called Spanning Tree Protocol. It's really simple to activate, and I'll show you right now on all of these switches how to do it. First, you want to enable them, and for this example, I only have one VLAN, so it's going to be pretty simple to explain. So, spanning tree VLAN 1, because that's the default VLAN, and there we go. Let's get this in real time now, and let's go ahead and do the same thing on this one. Oops. Spanning tree VLAN 1, and then same thing on this one. Spanning tree. Oops. So now we have all of these switches configured with spanning tree. What they're doing is they're negotiating packets called BPDU, which stands for Bridge Protocol Data Units. And these are some really cool packets. And basically what they're doing is they're negotiating who has the lowest MAC address, who has the highest priority number. In this case, they all have the same priority number. Maybe we'll talk about that in a future video, but right now it basically just, you can manually set that to determine which switch should become the designated root bridge. And in this case, one of these two have become the designated root bridge. The way we can tell that is the switch that has a blocked port on it, which is right here, is what is actually going to prevent the broadcast storm from happening. So we never get that issue where they just keep sending packets to each other forever and ever and ever. Because, I mean, obviously that's not productive for a network. And here we have switch 3, and let's look at its MAC address. So we look at FA00 and it's 0.05, and this one is 0.005 for both of these interfaces. And the way we'll decide is usually it adds together the priority, the VLAN, and the MAC address. And in this case, the VLANs are the same, the priority is the same, so the MAC address is what's going to determine what the root bridge will be. And in this case, it looks like it has become router 3 because it has the lower MAC address. Let's have a look at it. So show spanning tree. And yes, this is how you can usually tell in most situations that it has become the root bridge, because all of its ports have been designated to forward. Hello, this is Brandon Post, and I realized in the video I never said that you can literally just look up in this like little table and it tells you that this is the root switch. I don't know why I didn't mention that, but it's like that for all of the switches, and you can just go ahead and look up and it tells you what it is. Anyways, enjoy the rest of the video. So anything that it receives, it will just forward out of all of its interfaces. Depending on where it needs to go. Obviously, if this guy sent a packet here, it's not going to send it back out to him. But this guy will always just forward packets no matter what. And that means that he is the root bridge. And if we look at this one on switch 2, by the way, I will have a link to this exact packet tracer file in the description. You can go ahead and mess around with it and check it out. I would highly recommend doing this because me explaining it is not going to be enough to really learn how this works. And here we can see we also have 2 designated ports to just forward anything, and then a root port. And what the root port does is it wants to forward on the best path to the root bridge, which in this case is switch 3, and as we can see, this is FA03. That is the fastest way to get to switch 3. And now the last thing I want to look at is the switch 1, because this one is kind of the most interesting. We can see it has a blocked port over here, and that's this one right here, FA00. This is to block any to make sure broadcast storms don't happen like we just saw, and how to get to the fastest route to the bridge, or to the root port, the root bridge, sorry. And the way it does this is it determines each of these numbers here. I'll just write them in for you really quick. Let's put them up here. So for 100 megabit per second connection, that is going to be 19, it just has a weight of 19 to keep it simple. And then if we have a gigabit per second, that is equal to 4. And then 10 megabit is equal to 100. And basically, the routers, or the switches, sorry, want to find the most efficient route to get to the root switch. And as we notice here, from this switch to get to this switch, it is only 19. But if it wants to go through here, it's 19 plus 19, which is going to be higher than just 19 by itself because it calculates each hop by itself. But let's look at one interesting little feature here. I want to demonstrate if we have a gigabit link over here. Let's go ahead and delete this one and this one. And let's connect to the gigabit link. You have 01 over here, and then same thing over here. All right, now they're negotiating spanning tree protocol again. And now, as we can see, the port changed. The one that is down now. Why? Because let's have a look. This one should still be the root bridge. So show spanning tree. Yep, this one is still the root bridge, but as we can see now, it has a cost of 4 instead of 19 as it was before. And now switch 2 is the little guy over here. To send out gig 01, it's 4. And then to send out this one, it's also 4. So that means that this path is only 8 versus this path, which is 19. So even though there are more hops, this is technically a faster path for spanning tree. So it's really cool. That's basically a high-level explanation of spanning tree and how it decides which port is which. I know for DePaul you use this in Net363, but over here, let's go ahead and ping some of these routers or some of these end devices over here. So first, let's ping the server over here from PC0, and let's go in simulation mode. Okay, there's the packet. Boom. All right, sends it out there. And as we can see, because it sent it out this interface, it got dropped because this interface is technically down. So sends it out here, and this PC is not supposed to get it. So then it goes back out here, and let's see. Server 0 gets it, sends it back out, the route it came through, and boom, that is a successful ping. It learned how to get to server 0. I hope that helped explains spanning tree protocol in simple terms. Sorry if I was repeating stuff. I just wanted to make sure that it gets down into your head about how spanning tree works. I'd recommend downloading this lab. I have it set up in a file in the description, or not in the description, in the pinned comment is where I will put it. You can access it there. So go ahead and mess around with it. But now let's hop into CML and let's understand how it works in CML. All right, welcome back. So as you can see here, I'm in CML. This is the first time I've actually done a lab on this channel in CML, and I have the exact same thing set up. I put in all the switches and routers, as you can tell, it's very different. I mean, obviously you can't tell which device is connected to which, or you can't tell like which port is down. It's not as, I would say, verbose visually as Packet Tracer is, but it's more realistic to like what it was in the LAN Lab. Even though we can't see the actual like physical cables, like the Ethernet cables, this is as close as we're going to get for now as actually simulating the LAN Lab itself. So here we have the 3 switches plugged in, and as you can see, I already went ahead and set up spanning tree protocol on them. It works the exact same way in Packet Tracer, and here you can see like these are all gigabit Ethernet links instead of fast Ethernet links. CML is more updated, so I would say it's honestly better for these types of labs, especially for troubleshooting, because it's more realistic. But inside of CML, we can see on switch 2 over here, so this switch right over here, that this port is blocked, and every time we send out a packet, it will go through this route. Hard to tell exactly how it's going because there isn't really a reliable way, unless like we set IP addresses on the switches and do all this stuff. So all we know is that the packet can make it to the other device, from this device to this device. It's just more difficult than in Packet Tracer to be able to determine where the packet is going, because we can't go in simulation mode. This is how it would be like in the real world. But from what we can infer, on switch 2, this interface is blocked over here. On switch 1 up here, they all forward. So switch 1 in this case, because it has a lower MAC address, most likely became the root bridge because it has all of the designated ports here. Here we can see the priority and the address, how often it does the hello times, and here we can also see the priority. As you can see, they are the same. The address is slightly different though. Same thing for switch 3. Yeah, the address is just slightly different, and that is what determines here the root ID and the bridge ID. That is what determines which one will be the root bridge. In this case, switch 2. So this part is a bit short because I already explained all the details in Packet Tracer. I just wanted to kind of emulate how it would be in an actual like LAN Lab environment, since I'm not able to be there today. But this is how it looks like. I'll let you guys know how the Ubiquiti switches and the Cisco routers, like how they're coming in, and then I'll demonstrate like how to set them up. I'm very excited for them to come in because I really want to work on them. But thank you guys so much for watching. I'll also include the YAML file for this exact lab. As I said before, Packet Tracer was better for actually visualizing what was going on. CML is more like how it would be in the real world, where I just kind of have to look at the ports, like this one's blocked, so I have to infer that the packets will not be sent through here. So it's a slightly different than Packet Tracer just because the MAC addresses are different, but it's the same concept. So go ahead, download these labs, mess around with them. I hope you enjoy this episode. Next week, we're going to be going over OSPF, I'm pretty sure. I need to check what I have written down, what I've been planning, but I'm pretty sure it's OSPF. So stay tuned for that. Also, thank you guys so much for 2,000 subscribers. I was not expecting this channel to grow this fast. I thought I would just be doing like tutorials for students at DePaul, but I'm so happy so many people enjoy networking, and I'll keep trying to make these videos better. I'll bring in some more hardware, and yeah, that's all I got for you guys. Thank you guys so much for watching. I hope the audio quality is way better and the video quality. But thank you guys, and I'll see you in the next episode. Bye-bye.